Welcome to Daemon Automation's Factory Floor AI podcast series
where we break down real stories of how manufacturers are eliminating downtime, boosting throughput.
and solving costly automation problems using AI that runs on the equipment they already have.
Today, we're going straight into the thick of it, an industrial setting, a massive timber mill. And we're tackling a problem that, honestly, has stumped the wood products industry for ages: reliable outdoor automation.
Yeah, it's a tough one.
Specifically, we're zooming in on the Wavefeeder. It's also called a step feeder sometimes.
Mhm.
Critical machine, moves raw logs.
Absolutely critical, and historically almost impossible to automate reliably, especially outdoors. Operators basically said, technology just can't handle this.
And that wasn't just an annoyance, was it? This was costing them money.
Oh, big time. Before the solution, that wave feeder, it was the single biggest drag on efficiency in the whole mill, required constant manual intervention.
You mean someone standing there all day?
Pretty much. An operator spending their entire shift doing like industrial triage, pushing buttons thousands of times a day just to stop the line from jamming up completely.
Wow, thousands. That's basically a full-time job just managing failure. So today we're digging into how that conventional wisdom got flipped. Our mission is to unpack the core breakthrough, something called process variable fusion,
That's the key.
that turned this operational nightmare into a machine that actually set production records. So if you've got any equipment running in some chaotic, uncontrolled environment, you need to listen to this.
Definitely. This story has wider implications.
Okay, let's set the scene. What was the operational reality here? Why did this machine, which sounds simple, just moving logs, fight off automation so hard?
Well, the biggest factor location, location, location. It's entirely outdoors.
Right, not in a nice controlled factory setting.
Exactly. And traditional automation, like your standard photo eye, it relies on a single precise beam of light. You break the beam, something happens.
Simple enough, usually.
Usually. But outdoors, the environment itself just constantly messes with that single point of data.
And I imagine a timber mill yard,
Yeah.
that's probably the worst place imaginable for sensitive optics.
It really is. Think about it. You've got changing sunlight intensity, right?
Hmm.
Intense glare bouncing off wet logs or puddles.
Blinding.
Totally. Then rain, sleet, snow, even fog. Any of those can just block or scatter the beam, making the sensor think something's there when it isn't, or vice versa.
False positives, false negatives.
All the time. And that's just the weather. Then you have the product itself. These aren't uniform widgets, they're logs.
Natural shapes.
Yeah, curves, crook, taper, sweep, bark falling off, all inconsistent. And then there's the dust, sawdust, wood chips, dirt. It gets everywhere.
Clogging up the little eye the sensor looks through.
Precisely. It gets baked on, frozen on, you name it. So the sensor is constantly, like you said, crying wolf or just completely blind.
So if glare hits it wrong, it thinks a log is there, stops the line unnecessarily.
Yep.
Or if sawdust blocks it, it misses a log that is there, and then downstream, Jam City.
Jam City, exactly.
Yeah.
And the consequence for the mill, it was just crippling.
How so?
Well, massive labor waste, for one. Maintenance crews were constantly out there, cleaning sensors, realigning them, replacing them. It was a huge time sink.
Just fighting the symptoms.
Right. And the operators, they couldn't trust the automation, so they ended up running it in manual or semi-manual mode most of the time, just overriding the faulty signals to keep things moving, however inefficiently.
Which goes back to why I was losing money every single day.
That's the core of it. Constant failures, constant manual overrides. It throttled the entire plant's throughput. So this pattern of failure, it really forced a rethink. The traditional approach just wasn't cutting it. Relying on that single point of data in such a messy place, it was doomed.
Okay, so what does a good human operator do differently? They're not looking at one beam, obviously.
Exactly. It's about context, not just a single data point. A person sees the whole scene, right? They see the log shape, how it's sitting, where the chain is there room downstream, what's the weather doing, all at once. They integrate it.
So the solution needed to mimic that. See the bigger picture.
Precisely. That was the Daemon AI insight. Instead of one beam, let's use vision. Let's look at the entire area, hundreds of thousands of pixels, just like the human operator does.
Okay, but that sounds like it needs fancy cameras, special hardware. Putting sensitive tech out there in the rain and sawdust seems like trading one problem for another. How'd you get around that?
Well, that was actually one of the smoothest parts. We didn't need new specialized hardware out in the elements. It runs on standard off-the-shelf IP cameras that support RTSP. And guess what?
The mill already had them.
The mill already had them, often for security or just general oversight. So we tapped into those existing video feeds. No fragile custom sensors to get smashed by a log or corroded by the weather.
That's clever. So basically, if a supervisor could sit in the control room and see the wave feeder on a monitor,
Then Daemon AI could see it too. Same feed.
and because it's analyzing the whole image, not just one point,
It's much more robust. Glare might wash out one part of the screen. But the AI can still see the overall shape of the log, its position, the chain movement, the context. It learns to ignore the visual noise.
so it can adapt. Unlike the photo eye, which is just on off, blocked unblocked.
Exactly. It can adapt to those changing conditions that would absolutely guarantee failure for a simple sensor. It sees the whole picture.
Okay, so you've got the vision system tapped into the existing cameras. It can see like a human. How quickly could the mill actually make the switch?
Hmm.
Training an AI sounds intensive.
You know, it was surprisingly fast. The initial setup and training, just a few days.
Really? A few days.
Yeah, we needed one systems integrator, someone who knows the mill's control systems, and then just a handful of video clips.
Cups of what?
Just the Wavefeeder doing its thing, running in different conditions. Bright morning sun with glare, maybe a rainy afternoon, logs flowing smoothly, logs jamming a bit. Just examples.
To teach the AI what normal looks like and what different situations mean.
Exactly. Teach it the basic pattern, the cadence of the flow.
So walk us through that basic logic. What did the AI learn to do just from watching?
Okay, fundamentally, it learned to recognize instantly when a log starts moving onto that conveyor. It tracks that log.
Sees it enter the zone.
Right. It watches the transition. It knows when the machine should be in a go state versus a stop state based on the visual cues. And critically, it learns to only feed the next log in when the area downstream is actually clear and ready for it.
Preventing those jams caused by feeding too early.
Precisely. That's the visual flow control part. Seeing the log, seeing the gap. Basic but essential.
But you mentioned turning this into a record setter. That sounds like more than just avoiding jams. This is where that breakthrough comes in. Process variable fusion.
This is where it gets really interesting, yeah. Process variable fusion. Think of it like this. The vision system gives the AI its eyes. Process variable fusion gives it a speedometer, too.
Eyes and a speedometer. Why does it need both?
Because just seeing isn't always enough for optimal timing. Imagine the Wavefeeder looks visually identical in 2 moments, log here, gap there. But if the downstream conveyor chain is running super fast in one scenario and really slow in the other, should you feed the next log at the exact same visual cue?
No. Probably not. If it's fast, you might need to release the log earlier. If it's slow, you wait longer.
Exactly.
So the AI needs to know how fast things are moving downstream.
Precisely. Process variable fusion means the AI combines what it sees, the visual data from the camera, with specific process data from the machine itself.
Like the conveyor speed.
Exactly like the conveyor speed, it gets that information directly from the machine's brain, the PLC, the programmable logic controller. The PLC knows the chain speed.
So the AI isn't just watching, it's talking to the machine control system.
It's integrating context, visual context plus operational context, eyes plus speedometer.
Okay, let's make that concrete. Use the example you mentioned earlier, the go early feature. How does that work with the speed context?
Right. So say the downstream chain is running flat out, maybe 500 feet per minute, really moving.
Okay.
The AI sees the visual cue to potentially feed the next log, but it also gets the speed data from the PLC. It knows that gap is closing super fast, so it makes a decision, go early.
Yeah.
It releases the next log maybe 10, 15 feet before the absolute perfect visual alignment point.
Because it calculates that the momentum will carry it into the perfect spot just as the gap arrives.
Exactly. Proactive feeding based on speed. Now contrast that. Same visual picture, maybe an identical looking log and gap, but the PLC says the chain is crawling at, say, 50 feet per minute.
Right.
If the AI released the log 10 feet early now, disaster. It would slam into the log ahead or cause a jam. So in this context, the AI waits. It waits for the absolute standard visual go position, ensuring perfect placement for the slow speed.
So the same visual scene triggers two completely different actions based purely on the speed data from the PLC.
That's process variable fusion. It allows for incredibly nuanced, optimized timing decisions in real time. Decisions that before only a really experienced, focused human operator might be able to make consistently. It applies that optimal logic, informed by both vision and speed, every single time.
And that consistency must be where the performance gains really came from.
Mhm.
What were the immediate results for the mill once the system was up and running and stable?
The results were, frankly stunning. Almost immediately after they stabilized the system, the facility started setting new production records, facility-wide.
Wow, not just on that one machine.
No, because that wave feeder had been the bottleneck. They eliminated those sporadic failures, the inconsistent flow. They found speed they didn't even realize they had.
And what about those chronic headaches, the photo eye maintenance calls?
Gone. No more calls about glare blinding the sensor or sawdust clogging the eye. That whole category of maintenance nightmare just vanished.
So the wave feeder didn't just get faster, it got reliable.
Incredibly reliable. And maybe the most impactful metric, thinking about the human side.
Hmm.
We saw a 90% reduction in manual adjustment.
90%.
90. That operator who used to stand there pushing buttons thousands of times, they were freed up.
To do what?
Manage actual exceptions, focus on safety checks, take on higher value tasks. Their job became less about fighting the machine and more about overseeing production. It was a huge quality of life improvement for them, too.
That's huge. What about accuracy? You mentioned different speeds. Did it work well across that whole range? Was it just good at top speed?
No, that's the beauty of the Fusion. It maintained, I think it was 95% accuracy across all the process bands, slow, fast, medium,
Huh.
because it wasn't locked into one timing strategy.
It adapted.
It adapted its decisions based on the real-time context, the visual, and the speed. Before, operator fatigue or slight misjudgments would cause dips in performance at different times. The AI delivered that perfect, continuous consistency, regardless of speed.
So, summing it up,
Yeah.
the mill went from having its most inefficient, manually intensive problem child machine
Yeah.
to running it fully automated, minimal input needed, and it became a predictable, record setting part of their line.
Mm.
Operators are happier, maintenance is easier, a total transformation.
It really was. And I think the success story here with this timber mill wave feeder, it proves something really powerful. It
Mm.
shows that AI vision, when done right, can operate reliably in these incredibly messy, chaotic, changing environments.
Places where traditional sensors are just guaranteed to fail.
Exactly. Outdoors, dealing with natural, inconsistent materials, weather, it's the ultimate test case. It shifts the whole question from can we put a sensor there to can we teach a system to understand the context?
Yeah, that's a big shift. This clearly redefined what that mill thought was even possible with automation.
Absolutely.
So that brings us to our final thought for you, the listener. If AI, using this process variable fusion, can reliably manage a complex outdoor log wave feeder with constant glare, rain, dust, and weirdly shaped logs, what impossible automation challenge exists in your facility? That one piece of equipment you've always assumed needs a human babysitter, maybe because the environment's too harsh or the process is too variable, could teaching a vision system to think in context be the key to unlocking it?
This is what intelligent automation looks like. To learn more, visit damonautomation.com.